Good day, everyone. How are you doing? I hope you are all doing fine. So, in our lesson today, I'll be teaching you how to identify the amount of heat that was being that was absorbed by a substance or that was released by a substance. You'll be needing the following. You'll be needing a marker, a paper, and of course, a calculator. Okay, so let's start. So let's recap first a certain idea. In our previous lesson, we have learned that heat can directly affect the temperature of a substance, which means, for example, if you have a certain substance with a certain temperature, let's say we have a container filled with water, and that water has a certain temperature. So when heat is added or removed, it will of course affect the temperature. So basically, we know that when heat is added, it will increase the temperature of the substance, in this case water. And when heat is removed, it will of course decrease its temperature. So that is basically how heat affects the temperature of a substance. Now, also, we have learned from our previous lesson that different substances needed a certain amount of heat for a given mass in order to change its temperature. So I'll repeat, we have learned that the amount of heat, or there's a specific amount of heat needed by a certain amount, in this case mass, in order to change the temperature. And these variables can give us what we call the specific heat. So to sum up everything that I've said, specific heat is the amount of heat needed by a certain mass of a substance in order to change the temperature. Again, specific heat is the amount of heat needed by a given mass in order to change the temperature, which is mathematically expressed by C is equal to the amount of heat divided by mass times delta T. Or in short, we have this. C is equal to Q divided by M times the change of temperature. So let me show you a table. So this is the table. So let me explain to you what this table is all about in relation to our formula. So based from this table, we need, for aluminum, we need 910 joules of heat to change the temperature of 1 kilogram of aluminum to 1 degree Celsius. For copper, we need to add or remove 310 joules of heat to change the temperature of 1 kilogram of copper to 1 degree Celsius. For iron, we need to add or remove 470 joules of heat to change the temperature of 1 kilogram of iron to 1 degree Celsius. Last one, if you want to change the temperature of water, 1 kilogram of water to 1 degree Celsius, you need to add or remove 4,190. So basically, these numbers here are the amount of heat that you need to add or remove if you want to change 1 kilogram of these substances, or the temperature of 1 kilogram of these substances to 1 degree Celsius. Now, here's the thing. What if, for example, the amount of substance that I have is no longer equal to 1 kilogram, and the change in temperature is not anymore 1 degree Celsius? Because if the amount of substance is equal to 1 kilogram and the change of temperature is just 1 degree Celsius, we don't need to compute for anything. We just look at this table. But what if the mass and the temperature are no longer equal to 1? So how do we solve for it? So basically, what we can do is to rearrange this equation in order to solve that kind of situation. Again, wherein the mass is no longer 1 kilogram and the change in temperature is no longer equal to 1 degree Celsius. So, how do we use this formula to solve the problem? Okay, so what we can do is, from this equation, which is C is equal to Q divided by M delta T, what we can do is we need to do something to let this Q, or the amount of heat, to be by itself on this side of the equation. So we need to remove this M times delta T. So how do we remove this and place it to the other side of the equation? We just simply need to multiply both sides by M delta T. M delta T. So we can cancel this and this, and what we only have on this side of the equation is the amount of heat, which is now equal to M delta T C is equal to Q. Now, since our symbol here is equal, it means to say that the left side of the equation is equal to the right side of the equation. So we can interchange them, because some people, or most of us, are used to having only one variable on the left side and the other variables on the right side. So we will be having Q is equal to M delta T C. Now, since all of these three variables, the mass, the change in temperature, and C, are all in the multiplication operation, we can place them in any order. So we can have like this: Q is equal to, let's say, M C delta T. They are the same. Or we can have Q is equal to, let's say, C M delta T. Again, they're just the same. Or we can also have, let's say, Q is equal to M C delta T. So basically, these three equations are all the same. Okay, but the most common formula that other reference use is this one, okay, which is Q is equal to C M delta T, or the amount of heat is equal to the specific heat times the mass times the change in temperature. Again, bear in mind, these four are all the same. Okay, so we will use this one as our equation. Okay, now On the next part of the video, we will now apply this formula to solve the problem that I mentioned a while ago, wherein we want to know how much heat do we need to add or remove in order to change the specific or the specific mass of a substance to a specific temperature. Again, the questions that you will see on the next part, the substance is no longer equal to 1 kilogram and the change in temperature is no longer equal to 1 degree Celsius. So how do we solve for the amount of heat absorbed and release? Okay? Okay, so let us now take a look at the first problem. Okay, so in this question, it is said that the temperature of a 3.35 kilograms of water changed from 24.5 degrees Celsius to 26.4 degrees Celsius. The question is, how much heat did this sample absorb? Knowing that the specific heat of water liquid is 4,190 joules per kilogram degrees Celsius. Okay, so the idea is, again, you have a certain water, okay, at a certain temperature. So this amount of water is assumed to be 3.35 kilograms of water, and from 24.5 degrees Celsius it increased to 26.4 degrees Celsius. So definitely, if temperature increased, the heat was absorbed. So the question now is, how much heat was absorbed? Okay, so the first thing that I always emphasize to my students in solving any questions like this is to first identify the given. So from this question, the given are as follows. The mass of the given sample of water is 3.35 kilograms. Okay, next, the change in temperature, which is equal to the final temperature minus the initial temperature, is this. The final temperature is 26.4 degrees Celsius minus 24.5 degrees Celsius. So subtracting the two, we will have 1.9 degrees Celsius. And the last given is the specific heat of liquid water is 4,190 joules per kilogram degrees Celsius. So these are the three given. Okay, now we use the formula again, which is Q, the amount of heat, is equal to the specific heat times the mass times the change in temperature. So we have Q is equal to the specific heat, which is 4,190 joules per kilogram degrees Celsius multiply by the mass, which is 3.35 kilograms, multiply by the change in temperature, which is 1.9 degrees Celsius. So we cancel the units, kilogram to kilogram. and degrees Celsius to degrees Celsius. And what is left is the unit of joules. So multiplying all the three numbers, our heat is equal to 26,669.35 joules. Okay, so what is the meaning of this number? It means that in order to change the temperature of a 3.35 kilograms of water from 24.5 degrees Celsius to 26.4 degrees Celsius, how much heat do you need to add? You need to add 26,669.35 joules of heat. It's a big amount, it's a large amount of heat. The final answer has a positive value. So if Q has a positive value, it means that the heat was absorbed. Which means that if the heat has a negative symbol, it means heat is released. So I'll show you that kind of answer for our second example. Okay. Okay, so the second question is this. How much heat has to be removed from 2.25 kilograms of water, liquid form, to lower its temperature from 25 degrees Celsius to 10 degrees Celsius? So again, the condition is we have a certain amount of water, which is 2.25 kilograms, and its initial temperature is 25 degrees Celsius. So assuming this is the initial condition. And heat was removed. Therefore, the temperature decreased to 10 degrees Celsius. The question now is, how much heat was removed to attain such condition? Now, in this question, the specific heat of water is also given, which is 4,190 joules per kilogram degrees Celsius. So we can always check the table that I presented previously if in case the specific heat is not given. So again, refer to the table if the specific heat of the substance is not given. In this case, it's given. Okay, so don't forget, the first step is always to identify the given. So let's do that one. So from the question, the given are as follows. We have the mass of the substance, which is 2.25 kilograms. And the initial temperature is 25 degrees Celsius. The final temperature is 10 degrees Celsius. So using those, we can get the change in temperature, which is final temperature minus initial temperature. 10 degrees Celsius final minus the initial 25 degrees Celsius, which will give us negative 15 degrees Celsius. Sorry for that one. Next one, we have the specific heat of the liquid water, which is 4,190 joules per kilogram degrees Celsius. Okay, so our formula again is this, which is Q is equal to specific heat times the mass times the change in temperature. So we have Q is equal to the specific heat, 4,190 joules per kilogram degrees Celsius, times the mass is 2.25 kilograms multiply by the change in temperature, which is negative 15 degrees Celsius. Don't forget to cancel the units. Kilogram, kilogram, degrees Celsius to degrees Celsius. Joules is the unit left. So solving for everything, we have Q is equal to negative 141,412.5 joules. So again, it's a large number. Now notice something different here. I said a while ago from our previous answer, if the amount of heat has a symbol of positive, it means that the heat was absorbed. But in our case, the unit or the answer is in negative, which means heat was released. Okay? So again, positive means heat is absorbed. Negative means heat is released. Okay? So let's now have the last example for this exercise. And this is the question. So we have this. How many joules of heat are needed to raise the temperature? So raise temperature, so means say we can expect the temperature will increase. So we can expect that the answer here will be positive because heat is absorbed. So in order to raise temperature of 0.11 kilograms of aluminum from 22 degrees Celsius to 55 degrees Celsius, if the specific heat of aluminum is 910 joules per kilogram degrees Celsius. So again, the specific heat is given. If not, refer to the table. Okay, so here is now our paper. So let me just place it here. Okay, so the mass based from our given is 0.11 kilograms. The specific heat of the substance is 910 joules per kilogram degrees Celsius. And the change in temperature is final temperature minus initial temperature. We will have the final temperature as 55 degrees Celsius minus 22 degrees Celsius, which will give us 33 degrees Celsius as a change in temperature. Okay, so the formula again is this. So plugging in all the given from our formula, the specific heat is 910 joules per kilogram degrees Celsius multiply by the mass, which is 0.11 kilograms, multiply by the change in temperature, which is 33 degrees Celsius, canceling the units kilogram, kilogram, degrees Celsius, degrees Celsius. The amount of heat that was needed to raise the temperature is equal to 3,303.3 joules. Okay, so notice that the Q or the answer is in positive, which means that heat is absorbed. Okay, so that's it for this lesson. So what we did was to identify how much heat is needed to either be absorbed or released if the substance is not equal to 1 kilogram and the change in temperature is not equal to 1 degree Celsius. So I hope you learned something today. And if you have further questions, you can reach me out. Okay? God bless and peace out.